This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Good afternoon, everyone. Thanks for coming to the tutorial session. In this tutorial, we'll be focusing on problems from block diagram algebra, and also we will be looking at cases for stability criteria and also finding out steady state error in a system. So let's start with question 1. So in question 1, we need to find out the equivalent transfer function model for the system from R of S to Y of S, where R of S is our reference signal and Y of S is our output signal. Okay? So what we need is to reduce all these block diagram into simple ones first, using the standard for block diagram algebra that is covered in the lecture. So let me give a recap of what is already covered in lecture. For a series connection of two transfer function models, let's say this is input U of S and this is output Y of S, the transfer function from of the equivalent block is given by, can someone tell me? It's G1, G2. If it is a closed loop system where you have C and G and you give a unity feedback to the system, and the transfer function is given by Cg divided by 1 plus Cg. In the case where you have another type of closed loop, where you have a controller here, and you have a feedback here, the equivalent transfer function for this case will be G divided by 1 plus Cg, right? So let's apply this one to this problem. Okay. So you can start from any direction, so I will start from this way. So I can see that this equivalent block is G1 divided by 1 plus G1, G2, right? And similarly, this one is equivalent to G4 divided by 1 plus G4, G5. So if you flow from in this direction, then the equivalent along this line, which I call this way, will be a multiplication of this one, this one, this one, and finally this one, right? So in this loop, it is equivalently, this one is equivalent to G7 in the top, and in the bottom it is the multiplication of all these 4 set of transfer functions, which is, let me write it here, which you will get my output Y of S by input R of S equal to, I can see that this will be sum of these two blocks, right? Which will be G7 plus G1 divided by 1 plus g1 g2 times g3 times g4 divided by 1 plus g4 g5 times g6. Is that clear? So why I do that? Because I first find the equivalent transfer function flow of this one, which I will put it here, which is this term in my solution. Make sense? Yeah. If you have any questions, please ask now. Yeah, I will repeat how you go with this one. You have internal loops in this one, so we will first solve for that one. Then you go from one direction, you can find an equivalent of in this direction. Then you solve for the final one. So what you do is you can use the building blocks as the one that you see in lecture, and use that 4 building blocks to find out the equivalent transfer function for this problem. Make sense? Let's go to the next question. For this question, we have given a system here where the system contains a delay term. This one is a delay term. Is it clear? Is it clear on the screen? Yeah. Where the delay term is a non-rational transfer function, and we have a plan model A by S plus S into S plus 1. We were asked to find out the closed loop characteristics equation of the system. Right? So for question 2, I have a reference signal R, a summation block, a delay term e raised to minus st, a plan model A divided by S times S plus 1, and a unity feedback and the output Y. What is the closed loop transfer function of this model? So the characteristic equation of the closed loop is the denominator polynomial of the closed loop transfer function, which means that the closed loop transfer function, which is given by y of s divided by r of s, is e raised to minus st times a divided by s times s plus 1 divided by 1 plus e raised to minus st times 1 divided by a divided by s times s plus 1. This comes from the same block diagram expression that we have already seen. Right? So when we simplify this one, what we will get is e raised to minus st a divided by s times s plus 1 plus e raised to minus st times a. Okay, so this is the closed loop transfer function of the system, and the characteristic equation is the equation here. If you look at the question, you can also see that an approximation of e raised to minus st is given here. Right? So you can actually get an approximate polynomial equation, which is a rational function of e raised to minus st. So you take this approximation, it is given in the question. An exponential has different approximation in mathematical theory. You can have different approximation. This is one such approximation of an exponential term, and we use this one to solve our characteristic equation. So what we do is we substitute e raised to minus st in the transfer function. So y of s by r of s will be 1 minus t by 2s divided by 1 plus t by 2s times a divided by s times s plus 1 plus 1 minus t by 2s divided by 1 plus t by 2s times a. Let's simplify the equation. What we will get right now will be a times 1 minus t by 2s divided by, this first term is s square plus s, right? This times the denominator term 1 plus t by 2 times s plus 1 minus t by 2 s times a. And the characteristic equation is the denominator of your transfer function model, which is given by the s square plus s times 1 plus t by 2s plus 1 minus t by 2 s times a equal to 0. Let's simplify the equation a little bit more. We will get a cubic polynomial equation which is given by t by 2 s cube plus 1 plus t by 2 s square plus 1 minus a t by 2 s plus a equal to 0. What I did is I write it as a polynomial equation where the coefficients are given by all these terms, a polynomial in S. Make sense? Now let's come back to the question. What we need to find out is determine the values of t and a such that the system is stable. So what we need is to find out for what values of a and t this system is stable. For that one, you can use the Routh-Hurwitz criteria. All you need to find out is the Routh table and look at the coefficients in that one. So if all the coefficients on the first column is positive, then you can say that for those parameters the system will be stable. So let's write down the table. Since the equation is a third order one, we will have 4 rows, and the first coefficient here will be the coefficient of s cube, and the second coefficient is 1 from the s, which is 1 minus at by 2. Here the first coefficient will be 1 plus t by 2, and the second coefficient will be the last term a. Right? How do we find out the value here? What we do is assume, I will write it here, assume it was a, b, c, d, then this term, this for s cube, s square, s1, this term will be minus 1 by c times ad, like this cross multiplied ad, minus this one cross multiplied bc. Right? So similarly we can find out here, this will be minus 1 divided by 1 plus t by 2 times t by 2a minus 1 minus a t by 2 times 1 plus t by 2. And this term, since we have zeros here, okay, this is the first column, so that don't get confused. The second column term will be 0. We can show that in this case, this term will be d itself when you apply the same thing directly. How do we get d here? Why? Because this term will be minus 1 by the term here. Let's assume this term is x for simplicity. Minus 1 by x times, then you have zeros here, then you do 0 minus x d, which will give you d again, right? That's how you got d term here. Similarly, for this S0, you get the coefficient a here. Make sense? For system to be stable, you need all the terms in this first column to be positive, which means that you need t by 2 greater than 0, which implies t should be greater than 0. This means t by 1 plus t by 2 greater than 0 or t greater than minus 2. That is these two. And the third one will be 1 divided by 1 plus t by 2 times t by 2a, which is minus 1, sorry, minus 1 minus a t by 2 times 1 plus t by 2, this one greater than 0, right? Which means that minus t by 2a plus 1 plus a t by 2 times 1 plus t by 2 greater than 0. And we can actually expand this equation and say that for all those values which satisfy a and all those values of a and t that satisfy these four equations, which is 1, 2, 3, or 3 is this one, and the fourth one is a greater than 0, which comes from here. For those values of coefficient that satisfy this relation, yeah.
I still think have one more condition. It's 1 minus 80 by 2.
Yeah.
Should be bigger than 0. Because the RW array's necessary condition is all the coefficient is bigger than 0.
All the coefficients on the first column greater than 0.
All the coefficient of polynomial is bigger than 0. Then you can use
Yes. So if we do that one, so we do root only if all the coefficients are greater than 0.
Yes, so
Right.
1 minus 80 over 2.
Yeah.
This term should be bigger than 0. Still one more condition.
I think so, yes. Yeah. Yeah, that is true. I have a little doubt on that one because as far as I can remember, root condition doesn't say prerequisite like that one. Root condition already considered that one, but I will cross-check that one in the lecture note. As far as I can remember, root condition, that one is for second order systems. But for systems above second order, I need to cross-check that one. I agree to you for till second order system, which is true, but I want to cross-check whether it is also true for higher order systems. Okay? As far as I can see, it's only the root criteria that I can remember of. Okay. Shall we move to the next question? Any questions on the previous one? Yeah. So for the third question, we have a closed loop system shown in figure 3. So we have a block diagram of a DC motor where capital K, J and K are there, which are the parameters of the DC motor, and there is an integrator here. So what it is asked to find out the initial value and final value of the output. Okay. So how do we proceed with this one? First we need to find out the transfer function, equivalent transfer function of this system. So I will first consider the internal loop, then I will do the external loop and find out the transfer function. For the internal loop, I know that the transfer function will be k divided by js all divided by 1 plus small k times capital K divided by j times s. Right? So that is the equivalent transfer function model of the internal closed loop, which I can write it as capital K divided by js plus small k times capital K. Okay. Now what we have is to find out the equivalent transfer function of the system. So we have the system R, then this equivalent model will be capital K divided by js plus small k times capital K. Then we have an integrator, the output, and the closed loop. The equivalent transfer function model of this one is again k divided by js plus k times capital K into 1 by s divided by 1 plus k divided by js square k s. Which means I have k divided by j square plus k s plus k as the transfer function of this system, which is y of s divided by r of s. Now the question asks you to find out the output for a step input. So y of s for a step input will be k times j square plus ks plus k times 1 by s, because that is the transfer function of r of s. So first question is find the initial value. Initial value is at time t equal to 0, what is the value? Limit t tends to 0 e of t, right? But from initial value theorem, I know that which is equivalent to limit s tends to infinity s times e of s. No, sorry. They asked to find out not the error, the initial and final value of the output. So which is actually y itself. This should be y of s. Okay, that was actually the question asked for, which means when you do this one, you get limit s tends to infinity s times k divided by j square capital K small k s plus k times 1 by s. This s and this k cancel off. When s goes to infinity, this one is what it is? 0. Because s is not going to 0, it's s goes to infinity. 1 by infinity is 0. Okay. So final value. Similarly, we know that the final value when is y infinity, which is given by limit s tends to 0 s times y of s. In that case, what we will get is, similarly we will get answer as 1. But if you want to apply a final value theorem, you cannot directly do that one. Don't directly, when somebody asks you to directly apply final value theorem, don't apply that one directly. Why? Because you need to check whether the system is stable or not. So in this case, the characteristic equation is given by these terms, and it's a quadratic equation for all positive values of j and all, the capital and small k. This one is stable. Under that condition, you can apply the final value theorem. So let's move on to the next question. Find the unity for the unity feedback system, which is given here, and g of s is also given here. We need to find out the steady state error, right? For this system, what is the equivalent transfer function model? Which will be g of s divided by 1 plus g of s, right? Which means that y of s divided by r of s is g of s divided by 1 plus g of s. For calculating the error, so what we need is, so in this case, the error is given by 1 minus or y r of s minus y of s, which is r of s minus g of s divided by 1 plus g of s times r of s, which is again 1 minus g divided by 1 plus g times r of s, which is equivalently E of s is 1 divided by 1 plus g of s times r of s. So this will be the transfer function of the error. So what we need is to find out the steady state error. So before we find out the steady state error, first we need to check whether the system is stable. For doing that one, let me find out the closed loop transfer function of the system, which is closed loop equation will be 1 divided by 1 plus 4 times s plus 1 divided by s square times s plus 2, and the power, which is equivalently s square times s plus 2 divided by s cube plus 2s square plus 4s plus 4. Now, in order to apply the steady state, find the steady state value, you need to apply the final value theorem. Before applying that one, you need to check whether this polynomial equation represents a stable one. So you have to apply the Routh criteria and check that whether that one is stable. So I am skipping that step right now. It will be shown. Okay.
Sorry, what's the expression number you just wrote down?
So I wrote down the close this value, right, which is a transfer function from here to here, right, from E to R or R to E. Make sense? Yeah. Now you look at the characteristic equation, check whether this one is stable. It turns out that this one is stable, so I am skipping that step right now. Now what you need to find out is apply the limiting case where limit t tends to infinity e of t equal to limit s tends to 0 s times e of s, which is equal to limit s tends to infinite in 0 s times s square into s plus 2 divided by s cube plus 2x square plus 4s plus 4 times r of s. In the question, you are given 3 different r of t. So r of s for this one will be 1 by s, this one will be 1 by s square, and this one will be 2 by s cube, right? So what you need to do is substitute each of these values here and compute the value for s goes to 0. I am leaving the computational step right now so that I can go to the next question and quickly explain that one, because we have 5 more minutes to finish off. Is that okay for you? Yeah. So in this question, we are given a system, a closed loop system like this one, where this is a derivative term, d of s. In this system, we have 2 inputs, which are from r and w, and we have an output y. So this is exactly what we have covered in our lecture today. So we need to find the transfer functions from r to y and w to y. For that one, first we need to find out the equivalent transfer function of this internal block. By using the transfer function algebra, we can do that one. Why? Because this one will be 1 by s square divided by 1 plus 1 by s square, which will be the transfer function of this internal feedback loop, and the total transfer function of this one. So which means this is exactly this expression. Now you can actually apply the algebraic equation that is actually we have covered today. So from that one you can find out the transfer function models from r to y and w to y, which turns out that are the sensitivity transfer functions of this system. Now when it is asked to, because in this case you have a constant k, and you have to look at for what values of k the system satisfy stability condition. In that case, what you need to do is you take the characteristic equation of the closed loop model, which will be, let's say this is c, and if this is g, it will be 1 plus 1. The characteristic equation will be given by 1 plus cg, and you compute it to 0, and you apply the root condition and find out the value of k which satisfy the stability criteria. And the next part of the question asks you for that choice of value of k, what happens to the steady state error to a step input of r of s, and also what is a steady state output value for a disturbance input, which is also a step input. So if you remember what we have covered in the last part of the lecture today, we have also done a very similar problem where we take a step reference and a step disturbance. This is equivalently the same problem. So if you are, due to lapse of time, I cannot cover that one, but the solution will be published in LMS. You can apply that one. So it turns out that solution will look like this one. So the transfer function model of that one is given by the equivalent sensitivity functions here, and you can find out the transfer function models for r to y as well as from w to y here. So finding out the steady state value, you apply the final value theorem. Before doing so, you need to check whether the system is stable for that value of k. In this case, it turns out that you will get a quadratic equation. So all you need to look is where you have constant positive coefficients for the polynomial. Similarly, you can also find out the steady state value of the output to a step input. That's all for now. You can try out the other problem. Here you are given a transfer function g for considering this loop, and you are asked to check whether these closed loop systems are stable or not using root stability condition. What you need to do is to find out the closed loop equation, closed loop transfer function for the given g. It will turn out to be g divided by 1 plus g, and you find out what is the characteristic equation for the closed loop transfer function, and apply g, substitute g for all these things, and find out, apply Routh criteria on the denominator. Yeah, that's all for today. Thank you.
Could you explain more how to get this one?
How to get that?
Yeah,
one?
yeah.
Okay. Let me take this off. So usually the session is for 1 hour, right? If I'm not wrong.
Yep, but we actually start
This is to finish at 3:15. It's fine.
15, yeah.
2:15?
Yeah.
Okay, because usually they do the recording, so I was asked to start 5 minutes late.
Yeah, okay. So how to get this one?
That's just Laplace.
This one, right? So what you need is you find out the transfer function model of this one, right? So output will be steady. You need to find out the steady state error. Error will be R of s minus y of s. Right? So here you have R of s minus y of s is given by this one times R of s. So it's g divided by 1 plus g times R of s, right? Which is 1 minus g divided by 1 plus g times R of s. You take the common term out.
Okay.
So when you compute this polynomial function, you will get 1 plus g minus g, which is 1 divided by 1 plus g times R of s.
Yeah. I got onto this section.
Yeah.
How to get this one?
Which photo? This one? Which I wrote down here. It will be actually uploaded to the LMS, so you can find out. This one? Yeah, take it, that's fine. Yeah, sure, take it. Yeah. So you get this one, right? Do you agree to this one?
Yeah,
This is your U of s.
Yep.
Now you want to first check whether the system is stable. So what you need to do is
Yeah, it's all positive. Yeah.
all positive.
So stability is determined by the denominator.
Stability is determined by the characteristic equation. So in this case, the characteristic equation is from the denominator.
It's
So
positive.
is it always from the denominator?
Always from the denominator. For example, if you take a transfer function g of s, let's say it is s minus divided s plus 2, how do you check whether the system is stable? Because the stability is determined by the poles of a transfer function, right? The poles is actually coming from the root of the denominator.
Yeah.
Because this 0 is actually 1, which is here. The pole is actually minus 2.
Yeah.
So if the poles are on the left hand plane, then the system is stable.
Yeah.
So the stability is only determined by poles. The poles comes as the root of denominator.
Yeah.
That's why we look at denominator.
Yeah. So you just set all of that equal to 0.
Why you put all of that equal to 0? Why? Because you need to look at the roots of the solution,
Yeah.
and that you can find out by putting it to 0.
Yeah. That's right. And then you just solve it for criteria.
You don't.
Yeah.
No, you don't solve it actually. So what?
So I'm sorry, like s plus 2 equals to 0, and then do this.
Yeah.
Yeah.
Exactly.
Okay.
Yeah. So once you get here, you get this equation. Then you find out the steady state error, because this one is this one times R of s, right? So the first one is 1 divided by 1 by s. Then so this is s times e of s times 1 by s. This s and s cancels off, so you'll only remain with e.
Okay.
Then you'd substitute s equal to 0. So this is 0.
Zero.
All terms are 0 because it is 0 by 4, which is 0.
Yeah, okay. And how to get this one price?
You- this 1 by s is the Laplace transform of step input 1, which is 1 by s.
Okay. And Laplace transform for t. Oh yeah.
1 by s square
and t
Two-
squared.
two
Oh,
by
okay.
s cube.
Thank you so much.
No worries. Hi.
Hi. I've got a couple questions.
Yeah.
First, with the sensitivity
Mhm.
transfer function.
Yeah.
So, in that example,
Yeah.
you get your two sensitivity transfer functions.
Yes.
And then you.
But basically, he doesn't call it a sensitivity transfer functions. But since you have actually did today's lecture, I just called that one. You can actually consider it as a transfer function for the output to one specific input. So when you look at this one, this is the solution. The system has, when you look in the system perspective, they don't call it as disturbance or reference or anything. If you look at this system, you have two inputs coming to the system from the external. One is your reference, one is some input disturbance. That don't bother about that one. But it's actually two if you call it a system block, there are two inputs coming to the system, which is R and W. And there is only one output coming out, right? Now you are looking at a transfer function of what happens to Y, to the system, how this R is mapped to Y, how this W is mapped to Y. That's what actually a transfer function does. A normal transfer function, if you have a system, you have an input, you have an output. A normal transfer function will give you an output equal to, let's say this is S of S times U of S, right? If it is S. Now you have two things, then it turns out that because of linear superposition principle, this is something times R of S plus something times W of S. Right? That's what you get here anyway. That is your Y of S. Now this something is actually the transfer function from R of S to Y of S when your W of S is 0. Similarly, for Ws, this is a transfer function from here to here when this term is 0. Because of superposition principle, these two you can actually add.
Okay.
Yeah?
And
That
then,
is that your question?
Yes.
Okay.
Yes, clarify. And then I have a question, which just needs to be taken back a step.
Okay.
So I
That's okay.
apologize.
That's okay. Yeah.
But I kind of struggle understanding,
Yeah.
like connecting the frequency domain to physical systems, I guess, and
Okay.
understanding what it is. So in the example where we've got
Yeah.
the room, the heating the room,
Yeah.
and you're measuring that over time,
Yes.
then like what are you taking into the frequency domain, and like what does it
So.
does it mean?
So it's actually, first of all, in this case, what we are trying to look at, we are looking the signals in time domain, right? And we are trying to understand what happens in systems in time domain. That's what we are actually currently doing. But in a later stage, you will figure out that it is easy to find out what happens in time domain if you look at what happens to the signal at the frequency domain.
And so when you say signal in this context,
Yeah.
is that like the temperature that's being recorded?
Yes, yes. So any time varying signals like R, W, and Y, all these things are my signals, and these are, you can see as an amplification of them. But I can actually say why it is so, but anyway it will be covered in the later lecture. What actually happens in a linear system is if you put something into a system, you get something out. Like that's what actually a system does in an abstract level. But a specific class of signals, which turns out to be sinusoidal signals, when you put a sinusoidal input to a system, you also get a sinusoidal output from the system.
So do you mind just explaining that in the context of the heating room system?
Yeah, so you cannot directly find a matching example in heating room example.
Okay.
But
Or just like a
yeah, so in heating room, what actually happens is you are getting some noise to the system, right? Let's say the noise is your heat coming from the door pathway or under the door. That will be anywhere that exists there. Assume that if your system is not capable of compensating for that disturbance, then you are actually failing at your control, right? So in a control system perspective, your designed controller, I think we should leave this place now. What time the next lecture starts? Okay. So I can explain in the way we walk out. Basically, in a system level perspective, the controller should actually compensate for the disturbance also. So there are actually, I would say, like in a typical classical control system, a controller has mostly 3 roles, like 3 or 4 roles. The first role is to ensure stability of the system. Like but it's not just sufficient to ensure stability. You may also have to get some performance of the kind of. Meaning that, let me just because I left anything there. So you need to look at how you get the time domain performance. Time domain performance.
Well, I missed Friday.